I had dinner between the last video and this one, so I might have forgotten what I just did. I think I was about to, if what I see on my board makes sense, I was about to use the Taylor series, or in the specific example, the Maclaurin series approximation, to figure out a polynomial version, a sum of polynomial terms, to approximate e to the x. And remember, let me write here what the definition of the Maclaurin series was, is that we said that f of x is equal to the sum from n equals 0 to infinity of the nth derivative of f evaluated at 0. I don't know if I remembered to put it evaluated at 0 last time I wrote this down, times x to the n over n factorial. And hopefully that makes sense to you. This might seem really confusing and strange, but now that we're going to apply it to e to the x, it should maybe be a little bit more concrete. And I think at the end of the last video I said, well, if f of x is e to the x, f of 0 is e to the 0, which is 1. And f prime of x, I mean, that's any derivative of e to the x is equal to e to the x, right? So you take any derivative at 0, and it equals 1 for e to the x, for this particular case of f of x. And that's really neat. That means that the rate of change of y with respect to x is, for every 1 you move in x, you move 1 in y. That's fine at e to the 0. But that also means that the rate of change of the rate of change is also 1, and the rate of change of the rate of change of the rate of change is also 1. So at e to the 0, or at x equals 0 of e to the x, the slope, and the slope of the slope, and the slope of the slope, and the slope of the slope, they're all 1, which to me tells me something is mysterious is happening. And it's another reason why you should just sit and ponder e. But anyway, back to what we were trying to do. So how would we do this? How would we write the approximation? Well, we could say that, let me write the approximate, I'll call that p of x, because it's going to be a polynomial. It equals, well, in this particular case, what's the derivative of any derivative evaluated at f of 0? Well, that term is 1. We wrote that down right here. F of 0 is 1. The derivative, the first derivative at 0 is 1. The second derivative at 0 is 1, right? That's what's special about e to the x. So all of these terms are going to equal 1, right? So this polynomial simplifies to the sum from n equals 0 to infinity of x to the n over n factorial. That, to me, is very neat. Remember, these are all 1 in every term, so that's why I took it out. So what does that mean? Well, that tells us that e to the x can be approximated, and actually, I don't prove it here, but it actually turns out that when you take the infinite sum, that the Maclaurin series not only approximates e to the x at x equals 0, when you take the infinite series, it actually equals e to the x. So when you take a Maclaurin series at 0, and the resulting function, the resulting polynomial, actually converges, and that's something we'll learn a little bit more rigorously, hopefully later, and when we start doing analysis. But it will it can actually converge to the function at all points, and it actually is the case with e to the x. So we can actually say that e to the x is equal. I didn't prove this, but you could take my word for it, and you could even test it out with some numbers. It equals this sum. Well, what is the sum? Well, it's x to the 0 over 0 factorial. Well, that's, so let me actually just try x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial, and you keep going. And of course, that's equal, so e to the x is equal to, x to the 0 is 1, 0 factorial, I said in the last video, is 1, so it's 1 plus, this is just x, plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, and you just keep going on forever. And that's e to the x. And to me, that is amazing, because this strange number e, this 2.7, whatever that we got from compound interest, it can be written as an infinite polynomial, this polynomial series or this Maclaurin series that actually has a certain beauty to it, right? This number is kind of ugly when you write it out, 2.7, whatever, whatever. But when you write it when you write it to an exponent power as an infinite sum, it kind of has a nice rhythm to it, right? It's a very patterned. Who would have guessed that you could have written it in such a simple form? And even more, what happens when x is equal to x is equal to 1, right? So what's e to the 1? Well, then we set x equal to 1 on both sides, and I think I have space to do it here. E to the 1, which is equal to e, we just set all the x's to 1, so we get that's equal to 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial. That, to me, once again, is amazing. That the number e, and we've just stumbled on another definition of e. E is equal to the sum from n equals 0 to infinity of 1 over n factorial. That is amazing. So now we have two definitions for e. We have this one that we stumbled on, and of course we had the ones from compound interest that I will do in magenta. The limit as n approaches infinity of 1 plus 1 over n to the n. That also is equal to e. This is starting to give me chills, because this very strange, bizarre number is popping out kind of. This might not seem so natural to you, but it's neat, and it comes out in compound interest and continuously compounding interest. But this is even simpler. I just keep taking 1 over the factorial of numbers, and I add them all together. And if I take every number really in existence and I sum them all up, I get e. That, to me, is amazing. 1 over n factorial of essentially every integer from 0 to infinity. If I sum them up, I get the number e. You hopefully are getting chills right now. Well, anyway, let's do the Maclaurin series for a couple more functions, and then we'll get to something that is even more mind-blowing. I'll see you in the next video.